what we're going to be going over here is a nonlinear programming example, at least for a nonlinear objective function here. And what we're going to be looking at is what they call the production function here. Now this production function, that's similar to the Cobb-Douglas production function that's widely used in economics. But we're going to take this production function and we're going to adapt it just to a single product that we're manufacturing. Okay, so this is what we're dealing with here. So let's get an understanding of this production function. So we'll break it down here. So let's break it down here by element here. So a Q here, that represents our output. And really that's the total production value that's being produced here. In our case, Q is going to represent the profit that we have here on a particular product we're manufacturing. And that this output here really depends on the inputs here. So let's just go through our inputs. So first, Y here, that's going to be our total factor, or what they may call the total factor of productivity, or some value. In our case, Y is going to represent the revenue we have here on a particular product. And you take that times, and we'll get into the exponents here, you take that times your material, and that's M here. That's the material, the input value here. And we'll just look at it in terms of the material that we're putting into this particular product we're manufacturing. And you take that times labor here. And of course that's the labor, the input value of the labor here that we're going to look at. And everything's going to be in dollars here, in units or dollars here. And you take that times K here, which represents the capital, again as an input. That would be your equipment, your buildings, and so forth. But in our example here, we're going to drop out this K capital here. It's really fixed in the short run. It's not variable, so that doesn't become a factor here. And if we drop that out, then we can look at it when we start plotting it. We can just look at two variables here, material and labor. Okay, so that's what we're talking about. But the other thing is here is these exponents here. This is the key to this whole production function, these exponents here. So I got them A plus B plus C here. Really what that is, and we'll get into it in our example, that's the share of the productivity of output by each one of our factors here. So, and those are exponents here. Those are whatever material is raised to an exponent A, labor is raised to an exponent B, and capital raised to an exponent C. But really these exponents here, they really should add up to a unit of 1 here. You break out your percentages here, that each one of these variables is the material, the labor here, and of course capital we're not going to use, is really the share of productivity, or the contribution here. We can go down here. That's the share of productivity, or the output here, or what each one of these elements here is contributing. Each one of these variables. Material is contributing a certain percentage to the revenue. Labor is contributing a certain percentage here to the revenue. So that's really what these exponents are here. So this is our production function here that we're going to be using. Okay, so let's go and let's apply it. Okay, so what we're going to do here is we're going to expand this production function really to calculate profit here. And in our terms, profit is going to equal our revenue minus costs here. So we're going to add in this cost into our production function. Okay, so this is what we're going to have. We're back to our production function here. Okay, so our profit here, that we're going to maximize this. This is what we want to do with our linear programming here. We want to maximize our total profit here. And it's going to be in terms of dollars here. And that profit equals, again, Q here. That was what? This is going to be our total profit here that we'll be looking at. And that's equal to, we calculate that by taking, we're going to use $1,400 here. That's that Y value that we're looking at here. That's that total factor of productivity, or the value here. So that's really going to be revenue in our case. So we're going to say when we sell this particular, let's just look at it in terms of one product here. When we sell that product, we're going to get $1,400 for that product here. So it could be like an industrial engine or something of that magnitude here, where it's actually you sell it for $1,400. So that's a per unit revenue price here. And then our material here, well, let's just look at it. This is what we're going to be solving for, material and labor here. So first off, for a material and that exponent, we're going to say that is 50% or 0.50 here. So that is going to, material here contributes 50% to our revenue. So that's, we're going to raise our material here to 50% or 0.50. And we take that, and of course the 1400 here is times material and labor. So then we add, we take and we multiply material times the 1400, but we're also going to be looking at multiplying our labor times. It's all one multiplicative amount here. So our labor here is going to represent 33% of the revenue, or that's what it's contributing to the revenue here, that $1,400 here. The labor amount, we raise it to the exponent of 0.33, or represents 1/3 here, or contributes 1/3 here to our revenue. And then what we're going to add in here that we typically don't see in this production function, we're going to subtract out our material cost here on a per unit basis. In this case, our material is for building this product or manufacturing this product that we're selling for $1,400. It's going to cost us $350 in total material, or a unit cost here in material. And then we also have labor here, and our labor to manufacture this product here that we're selling for $1,400 is going to be $200 here. So those 350 times whatever material unit materials we're looking at, less our 200 times whatever labor amount we're looking at. We're going to subtract those from our multiplicative or our production function here. So again, this is the case here. We're going to have this nonlinear objective function here. This is where we're going to maximize our profit here. That's what we're trying to do. We're using linear programming here. We've got this nonlinear objective function. Here we're going to try to maximize the profit here. And that's coming up with the right quantities of material and labor here. Okay, so we've got our objective function defined here. But we're going to add into that, we're going to have some linear programming constraints here. So what we're going to say here for that material and labor that we're have available here to manufacture this product, we're going to say we only have $40,000 worth of available funds here for material and labor here. So which makes sense here, because we've set our product cost here based on the $40,000 available funds that we have. So we're going to, our constraints here for a linear, we'll take 350 times whatever material amount plus 200, and these are dollar amounts here, $200 here times whatever labor we're going to come up with, has to be less than or equal to $40,000. That's available funds we have. And then we got one other a constraint here, and this can make sense here when you think of adding that in here. The adequate labor here for production here, we're going to say that we're going to need 3 times as much labor here value-wise as we have in material here. So that makes a sense too. If you're trying to determine how much material and labor you're putting in, you want to keep looking at that factor here. And so what we have for our linear program of material, we move our three times our labor over to this side of the equation, and we come up material minus 3 times our labor is less than or equal to 0. So those are the 2 constraints that we're putting into our linear programming here to maximize our profit. Okay, so let's move on here. Okay, so this is our objective function here. Again, I got lay it out here. Now remember, we raised that to 0.50 here and 0.30 here, and we subtract out our material and labor costs. These are the constraints. You enter them in just this fashion here when you put them into your linear programming. You wouldn't put the Q in, but this would be your objective function here. Okay, and then just laying it out here just to show that I have done this here, and I've done it in MapleSoft. You have to use a nonlinear linear programming. In this case, it's NLP solve function that you have in that program, and then you get your just same as you have here. I put in here at 50%, I just put it as a 1/2 here as an exponent here for material, and then that 1400 times our material times our labor, and I put it in as a fractional amount here as 1/3 or 33%. These can become critical here when you put them into your programming. You got to get the right decimal points and so forth, but the fractions give me the best solution that I can come up with in this case here. And then we're going to subtract out our 350 times whatever material and $200 here times whatever labor amount, and then subject to these constraints here. And then you have to assume that they're non-negative here. Those materials, labors, you have to say that they're greater than or equal to 0, and we're going to maximize it. Okay, so what I've done here, by running it through that that NLP solve function up above, I come up with our maximum profit here, $9,953. And then the material in units here, we're just going to say in material units, we're just looking at one product, 68.57 units, and then our labor, 79.99 units here. So however you define it, and we're just looking at it in terms of units, whatever you want to break that down into hours or dollars per hour or so forth, but in our solution, that's what we came up with. Okay, so there it is. I put it into, and we put it right back into that our objective function here, and you're going to come up with that amount here, 9,953. I'm just showing how you substitute these quantities back into your objective function here. And then one other thing here. This is where we had the built on our constraints up here for what we have for available funding plus our material and labor proportion requirements. If I put no constraints at all here, if I took those constraints off here, where you know those constraints that we were talking about up above here, and I just open it up, what you would come up with here, you're going to come up with a maximum profit of $10,162. And that's going to give you material units of 87.11 and labor units here of 101.6. And the only point I'm trying to make here, by opening that constraint up to whatever, just say we have no constraints here on the dollar amounts, that gives us tells us how many units we really can manufacture here without, in total here. So really what you're looking at, and I put it in this case here, if I put it back into my constraints here, I moved it from 40,000 up to 50,000. The key is here. No matter how much more money I pump or put in, if put 52, 53, 54,000, I'm going to get no benefit out of it here. I mean, you're not really spending the money, you're making it available, but I get no benefit. I wouldn't be able to build any more units than what I'm showing here, 87.11 and 101.6. But that's based on the exponents we have here for our materials and our labors and so forth here. And that's really based on the objective function here. Okay, so the next thing we're going to go out and we'll look at this, we'll lay it out in a plot and get some understandings here when we look at it, and looking at some 2D and 3D plots here to understand it a little better. Now we'll go over a solution here for our linear programming problem, and we'll look at it in terms of 2D and 3D plots here. Okay, so first let's start with our linear programming constraints, and remember we had those two constraints here. So what I'm showing here is our material is showing along our bottom axis here, x-axis, and our labor would be showing along our y-axis or vertical axis. And what we're going to have are those two constraints. First, for that funds that are available, the 40,000 here, that was 350M plus 200L here. So all you're going to do is just set one equal to 0 and solve for the other. So this is what the line you're going to get here for your $40,000 worth of available funds here. And then the other constraint was, remember that material and labor here constraint, M minus 3L is less than or equal to 0. So there's your constraint there. So and then you also had material and labor has to be greater than or equal to 0 here. Okay, so based on the constraints, this green area here would be your feasible area here that you're looking at. Okay, so that's for our linear constraints. Now let's go over here. Now this is the case here where when you're dealing with these non-linear functions here, where you got those fractional amounts with those exponents that you're looking at, times multiplying them together here, this is where you're going to get what they call equal product curves here. And really what they are is called iso-quant lines. This is where you have equal quantities or the same amount of output, or say whatever the output is. In this case it was that Q. But looking at them themselves, they don't give you a whole lot of information here. So what you're going to be looking at here, I'm just overlaying these over the constraints. So the great constraint area is what a feasible area here is that green area here. And just overlaying these equal product curves. And really what those equal product curves is, I just put it into the computer here, MapleSoft, and it's this equation here, that objective equation here, with taking our revenues times those exponential amounts here for material and labor and subtracting out our material and our labor costs, and you're going to get these curves here because it's built along the exponential factors here. And one thing I want to point out here, we maybe didn't mention it earlier, that material, we raised it to 0.50 or 50% here, represented of the revenue here, $1,400, and the labor here was 33%. If you add those up, they're going to come up to 83%. Now, typically when you're looking at these solutions, you're looking at 100%, but in this case, we are only looking at 83% here between material and labor and what they're contributing to the revenue here on a per unit basis. Okay, so they're nice to look at, these ISO quant lines here, but they don't tell you a whole, it's difficult to understand them, and you really have to look at them in 3D, which we're going to look at. But really, when we're getting down, you can put as many lines as you want here. These just represent many different amounts of output that you're looking, equal product curves, each amount of outputs. You can put any number of lines you want into the software package I have here for Maple, and I don't know, I put in 10 lines or something like that. So really up on the top here is going to be your maximum profit that you're looking at. And when you move down this way, you're going to have, we're going to be losing, or you'd have no profit here, a negative profit, which we'll look at. But what we want to look at here, we'll look at no constraints here, and that, remember, we come up against giving up to $50,000 or no constraints here, and we have to come up with a solution here versus the constraints. So no constraints I'm showing in blue, which really remove up to about $50,000 here in available funding, and after that, no additional funding is going to give us any more additional profit here. So you wouldn't, you're not going to use the money, but you're not going to, you don't need any more money than the $50,000 or $51,000, I think was our cutoff. And then red here would be based on our constraints. So let's just go and look at them here. Okay, so based on our constraints here, we're going to, this is where it is, and actually it should, we came up against our funding constraint here, that $40,000. So this is really our maximum profit here based on those constraints. Makes sense here. It falls on the line here. And again, you can see it's sort of falling in the middle of this first ISO curve here, because that's your maximum profit, and we'll look at it in 3D, is going to be up there, up in this area here. So it makes sense. It falls right in here, just as the computer plotted it out. And that was that point here, 68 M here. Again, our M material is shown here, labor is shown on this axis. That was 68 units of material, 80 units here of labor, and we had that $9,953 here. That was the maximum profit, the red here, and that's built off that objective function we have here. Then, again, we took off the constraints, and it moved up right here. That blue dot, that's the maximum profit here with no constraints, and that was what, 87 material, 101 labor units here, and that gave us $10,162. Okay, so just from that, you can see these ISO curves here. If you can interpret them here on a two-dimensional basis, you can see what we have here. So the difference you're really looking at is this red here. We come up against the constraint here, and then I put it in on a solution here. I pull that constraint out, all the constraints out, and I just come up with the blue here. This is the maximum amount that you're looking at here without any constraints. Okay, so that just gives you an idea of what you're working with here when you have the objective function you have with the exponential amounts here. Everything is built around these, what power or what fractional amount are you raising your material and your labor to here. And to calculate, that's a whole different subject when we start calculating these, and we'll look at how we'd go calculate both our exponential amounts for material, labor, and so forth here. Okay, so that's what we're looking at here based on our 2D lookout, our understanding here for our material and labor. All right, so now let's move over here in 3D and give us a little better understanding. So again, all we're looking at here is labor shown here, material shown here, but this is a surface plot here. So really what this surface plot is telling us here, what it represents is the profit, or that function that we're looking at. These are the all these equal product curves would be lying on this 3D curve here. So really what we're looking at, if we look at it in terms of our profit here, that Q or output that we have here in terms of profit, you can see here, this is our cutoff here, that zero amount. So if you project it over this way or across up this way, you can see this is where you're going to have, there's a point here where you have no profit here. So up in this area, this is where you're going to have your profit area here. And that would be some plus amount. And remember, we come up to about 10,000 here. So if we look at it, and anything, just make a point here, anything below it, when you're looking at those, your surface curve, anything below it here that you're looking at, that would be, no, you're not making any, you're losing money here if you are below that amount here. All right, so it gives you an idea what you're looking at in 3D here rather than just looking at numbers. So again, I've got the red one here, that little red, that red dot here, that's our maximum profit based on the constraints that we have, that we came up against that constraint that we looked at. We could look at it in our 2D constraint here as well. And then that blue dot, that was our no constraints. That's where we pulled our constraints off. That was our maximum profit there here. All right, so you can get an understanding here in 3D, and this is your profit area up in here based on what we're showing here. Down in this area, you're going to be running losses here. Okay, so that's first looking at it in our surface plot here in 3D. And then if we go down over here and just looking at it from a different profile here, our surface plot, you can see it again here. This is where you have, up here you have, that was our profit here, plus profit. Zero is this point here. So just projecting it, you'd have to project it in pictorial amount here along in this area. Just move that down here, and you can see you're having your profit up in here. And it's pretty level up in here, you can see it. Gives you a perspective of what you're looking at in terms of level curves, and maybe that's why equal product or level curves here. And again, that red dot here, that was our maximum profit based on that constraints we had. And then that blue dot here, that's where we pulled off our constraints, just to give an idea here. Again, just to look at it here. And again, remember, that's this function here that we have, our objective function. That's the plot of this objective function here. That's all all I did is I asked the computer to go to, I don't know, 150 both ways here, material and labor when it was plotted, and that's what it came up with. So it gives you a nice idea what you're looking at here. The surface plot is kind of handy and nice to look at here to understand what your function really is, in this case, that production function that we're looking at. Okay, so this is our surface plot. And then we can expand on that here, and taking that surface plot, again, with the computer here, I can just ask it to do those ISO quant lines here in 3D that we looked at. Remember up above here? These are those lines here if we look at it in 3D here. And again, same as our surface plot. Here's our zero up and above it. We're come up to our profit here, and I got around 10,000 here. Anything below that here is we're losing money, anything below it. Again, these are just based on those lines. And then if we go and look at our points here again, you can see I'm sitting out here in 3D here. Again, interesting to look at. This was coming up against the constraints, this red dot here, where we had a profit, I don't know, it was almost 10,000. Both of them were around $10,000. The only difference was a couple $100. And here was the blue dot. This is without the constraints. Again, nice to look at here in terms of your ISO quant lines, your equal profit or a quantity output. But you can see we're looking at your graph here. You have to look at your scaling on the graph here. In this case, we have 10,000 here up to max, a zero amount here, and then anything below it here, you can see the negative amounts. Again, that's based off that function that we're talking about. That's why you're getting these lines here. And then one last thing here. Let's just move over here. Again, I just tipped those isoquant lines here, those level lines. I just tipped them up a little bit just to get a little different perspective if you look into them from this direction here. Then you can see it again here. There's your zero profit. Here's $10,000. And negative ones are below here, those lines here. Just a different look at the 3D perspective. Again, the red dot here is maximum profit with the constraints. The blue dot here is, or sphere here, is without the constraints here. Again, based on this profit function, or the production function that we have shown down here. Okay, so it's good to have the capability of looking at these functions here in both 2D and 3D. Rather than just look at numbers, you get an idea where you're sitting here. So if you have the capability of doing this, it's good to do it so you understand where you're sitting here. So just for example here, you know, if we can look at it and you can see where your dots are here. If they were down in this area, you do whatever, you know, they can move all around here. But you can see based on our function here, up in this area, both on our surface plot here and our ISO quant lines here. And those ISO quant lines, we looked at it in 2D as well here. But with 3D, it gives us a pretty good perspective of what we're talking about when you look at your scaling factors on your vertical axis here versus, in this case, in all of them we had labor and materials here along our bottom axis. Either you look at XY coordinates or so forth. Okay, so pretty much this is our examination here of our linear solution here to our problem. But the point is here, the fact that we had constraints versus no constraints, there's really little or no difference here in the maximum profit that you're going to have built on our costs that are involved in material and labor that we're adding here. Okay, so that'll summarize our discussion here.